too, but he teaches math without bringing that old skibbity riz that Holloway brings every day. So, gosh, he's just so awesome. Here's where we left off, right? Correct? I assume is the last thing that I wrote down. What do we get for the jump then? You get pi. Everybody agree with that? Okay, so just to show that little bit of work in between, I'm just going to do it right here. This is pi fourths times what instead of dividing by 4? Ooh, I heard 4 over 1. I heard 1/4. Are you sure? I'm dividing by 4 over 1, right? I think you might have misheard the question or I misworded it. Everybody agree it does this? And what do we get then? Pi 16ths? Now, as we look at this, that's just 2 pi 8ths. And this is probably the one that I would actually go with. Why would I take the time to unsimplify or desimplify this expression? One more time? Because it's going to make it easy to add this, right? Now, as we go through this table, let's just check it out. If you add 2 pi 8ths to this, do you guys agree that I'm going to stay red here? You get negative 1 pi 8th. Add another 2 pi 8ths, and what do you get? 1 pi 8th. Add another one, you'll get 3 pi 8ths. Look at how nice this is, just centered right around the origin still. That's pretty convenient. And then we end with what? 5 pi 8. So I lied. Now it's not centered anymore. It looked like it was going to be, but it's not because I've been phase shifted. Cool. From these, I just want to call, I'm going to write these a little bit nicer, but I do want to call anybody out. Somebody is erasing stuff and adding them now. Would you be comfortable sharing your issue?
My jump was pi 8s, not pi 16.
Okay. Why? Do you know why you had pi 8ths?
I think in my mind I just added the 4.
Okay, that makes sense. Same thing happened to me. When I looked at this right off the bat, I wanted to add pi before I just did this because I tried to do what you recommended because I'm thinking about it and it's easy to get goofed up with mental math.
Can we not go off the jump real quick? I just want to write it down.
Absolutely. Okay, now once we've figured this part out, remember we set up our tables to give us the nicest possible values. On sine and cosine, we only get 1s and 0s and negative 1s, right? What's the only thing that we got on our parent yesterday if you look at the tangent x that we did initially? 2 undefined, and what were the other possible numbers? So there's a bunch that we saw, but they're not all nice. Look at the parent function from yesterday. We did a table with it. I got undefined and then only 3 numbers in the middle. Negative 1, 0, and 1, just like we did the previous, right? So something similar is going to happen here, but this thing has been made steeper. I can tell that because the 3 in front of the tangent, and it's been shifted up or down? Up. How many units? Good. Up 5 units. Now, there is a trend that we'll see clicks out here, but we should probably go through the whole process here. When I plug in this first one, and I wish I could zoom in further, anybody need more time with the period, the jump, anything like that before we actually start filling this in?
Why is the jump a pi over 16, and how does that become 2 pi over 8?
So if you simplified this,
Yeah.
sorry. Whoa, is this wrong?
I think maybe.
A pi 16th is not a pi 8th, is it?
No.
We're goofed up here. How many of you noticed that right away? Where's the mistake? Good call. If you noticed it, because I think you probably did, Rafa, is my guess. Or now you notice it. Is that right? So what do we do? Because good catch, by the way. Great catch.
Would be half pi over 8.
It'd be 1/2 pi over 8, which kind of is nasty. Would you guys agree? If only there were a way to fix this. Good catch. That's not true. 1/8 is not 1/16, or 2/8 is not 1/16. It's a 4th. So, with this, I'm going to go ahead and say, get out of here. I don't love erasing, but in this situation, I think maybe it's worthwhile to do. It's pi 16ths. We changed, and by we, it's me, I changed the wrong direction here. Pi 16ths works. Instead of trying to change that to something over 8, because I really don't want to do 0.5 pi over 8, because that seems awful, what else could I possibly change? I started at 3 pi 8ths, but just like Barsega had said before, and I made a mistake in doing it, but it's the same idea, it'd sure be nice if we had the same denominator. Could you write 3 pi 8ths or negative 3 pi 8ths a different way to make this a little bit easier to do? Let's call this one negative 6 pi 16ths. Great catch, Huggins. That was going to kill the problem, and we would have had a couple more awkward minutes of trying to figure it out. Negative 6 pi 16ths. Here, I got this for you. Aura. He's so cool. He's so cool. All right, are we sorted out here and it works? I just changed it to 16ths, right? Sorry, go ahead. Yep, because we had negative 3 pi 8ths, which was our left asymptote, I just doubled the top and the bottom so that I have over 16ths. So now this is going to be a little bit easier to do, I think, and it's going to make sense when we go to plug it in. Add a pi 16th, what do you get? Negative 5 pi 16ths. Negative 4 pi 16ths. That's a 16. Negative 3 pi 16ths. And one more gets us to negative 2 pi 16ths. Are these super nice values? Not really, but let's just check one thing. Let's see if maybe, just maybe, they eventually do wind up being kind of nice values. On this first one, what am I going to plug in for x when I actually evaluate this out? And I'm going to do 2 lines here. 5 plus 3 times the tangent of 4 times, what am I going to plug in here? Negative 5 pi 16ths plus, and I'm going to write this one out as just pi for now, but we're going to use 2 lines to work this one out, okay? Just to make sure we can see the work. I've just plugged in the appropriate x. Everybody agreed? All right. Well, help me simplify this. Would you guys call it negative 20 pi 16ths? Or would you simplify it first? What would you do, Makisha? On this one that my cursor's on right now, would you just call it negative 20 pi over 16? Or would you would simplify something first? What would you simplify?
4 and 16.
So 4 and 16, this becomes negative 5 pi over 4. If we simplify this fraction, negative 5 pi 4th, everybody cool with that? For real, or are you just nodding? Okay, I'm cool with that. All right, I just couldn't tell because when I said, for real, are you nodding, you just gave me the yes, which is something that I do to mess with people. And if you were messing with me, love it. All right, here we go. So this becomes 5 plus 3 times the tangent of, and I'm just going to think this out in my head. We already decided negative 5 pi over 4. I'm going to add a 4 pi over 4. I think I'm going to get negative pi 4ths. Now, here we are. There are nice values, and I'm going to try to do this here because I'm going to keep referencing this. I don't know if it's going to work. I'll just use this one. I always close my webcam thing because it makes me uncomfortable. All right, so this is what? Nope, there's going to be more awkward. I'm holding out my arms, right? So they've all seen it, but here we are. I want to think about this. Here I am at 0. Tangent of 0 is 0 because y is 0 over 1 is 0. Negative pi 4ths. I'm going to just move my arm. Here's 0. Negative pi 4ths is here. What's the x and y there? One's positive and one's negative, but we know it's, what are the actual values at the point? It's root 2 over 2 and negative root 2 over 2, right? Okay, one's negative, one's positive, but they're the same number. Guarantee this spits out what for that tangent? Negative 1, which is that nice value that we saw before. So, looking at this, there's one more line of work, and I will just make this table huge. This becomes 5 plus 3 times, what did you guys I guess it was just Abigail there, but I want everybody. What's the tangent of negative pi fourths? Negative 1. What's 5 plus a negative 3? 2. Okay. If you need this much work for every single one of them, is it okay? Yes. Do you think there's a way around it, though? I know that when I do negative pi fourths, the first value is negative 1. Like that happened on my parent function. When I did tangent of 0, what did it come out to be?
And why are we doing this, like, the whole equation instead of just, like, I mean, like, you can use your calculator, right?
So your calculator should act as a helpful tool, not as the way to do it. I have no issue if you use your calculator once we know how to do it, if that makes sense.
Yeah.
Like, I don't really care if you can use your calculator. This isn't calculator class. But there's certainly a time and place for it. Just not this time nor this place. Cool. All right. Check out this next one. I'm going to show one line of work, and I'm going to start separating these. But I think we can reason it out. All I really care about is what happens to the argument. So as I'm looking at this, if I did negative 4 pi 16ths times 4, do you guys agree it's negative 16 pi over 16? And then when I add a 16 pi over 16, which is just another pi, does it become 0? So check this out. It became negative pi fourths on the first one. Using only one line of work, you're going to see this happen every time as long as you pick your points correctly. I know this one's going to be tan 0. The next one, because this is always going to line up with our parent function when we set it up nicely, if you look at the parent function, we had negative pi fourths, 0, and what was the next one? Negative pi fourths, 0, and pi fourths. You can confirm this, and I would encourage you to do it. Don't just blindly trust it, but I don't even have to think it out because we've set this up with specific x values that will ensure that this happens. That's the whole point of finding the period and finding the jump. It guarantees these nice points. Did we do logarithms yet? We must have. We did the same thing with the arguments for logs, where it guaranteed that it was going to spit out nice values. So let's take just a moment. I want you guys to finish the very right side of this table. Cool. I'll come around and check values here for a second, or in a second. If you're watching this video on the road, one, smash that like button, subscribe, post this to your X, your Insta, your Snap, and then pause it and work through this and check your answers in 3, 2, you know what to do. There are shortcuts everywhere with this stuff, and I don't want you to just use the shortcuts if you don't understand how they work. You'll see them, and you'll start to connect them as we graph more of them. Check it out. When I get here, what is the tangent of 0? So it's the order pair is 1, 0, so 0 over 1 is 0, right? This really becomes 5 plus 3 times 0, which is just a 5. What's the tangent of pi fourths? 1. So this becomes 5 plus 3 times 1, which is 8. Now, I want to compare this with the one that we saw yesterday because I want to see something awesome that happens. Amplitude doesn't, I just spit a lot. Amplitude doesn't really make sense when you're talking about this because it's not a wave. I'm, however, still going to use amplitude to refer to this thing in front of the tangent function, just a number. And I want to notice something. On the parent, what was the amplitude? What's a number that I don't write here, but it does exist? 1. To get from my first my first actual point that's defined, what did I jump by in the y value? To get from negative 1 to 0, what did I have to jump by? Okay, I'm going to write in something else here in a second. To get from the next one to this, what did I have to jump by? Instead of saying 1, would you agree that it's just the amplitude? Like, it is the amplitude. Can you tell me the amplitude of this function that we're graphing now?
3.
So once you get your first point, we're just going to jump by the amplitude. And I can see this is going to work out. It's 2, and then the amplitude of 3 is give me to 5, and 3 more gets me to 8. We only really need 1 point. If you don't like that and you don't quite understand how that's working, that's okay. Cool. Let's graph this bad boy, because the hardest part of graphing these is, I'm just going to steal this in the notes to look a little different. We're going to call it pi 16ths, and I'm just going to replace it so I can see the graph. Okay. For graphing stuff, oftentimes the hardest part is picking your scale. And if you had to graph a bunch of different things together, it is and can be challenging. It doesn't have to be. Check it out. Here it is. And I'm going to actually make it a little bit lower just so I can see everything. Notice that I'm not even bothering to do anything below, right? I'm just showing almost no negative. And I'm going to make it a little bit more perpendicular. Okay, so here it is. I have to pick some ugly points. But as long as I'm consistent with it, it's going to be pretty nice and chill, I hope. Okay, give me the first furthest left point that you might put on here. Negative 6 pi 16ths. Now, if you want to call it this, I'm fine with it. Could you also call it, I don't know, 3 pi 8ths? Is it okay, whichever one you go with? They're the same number, right? It's just we unsimplified it. Okay, now you could try to like reasonably go through and check this out, but I think we'll be okay. Where's the second one go? If this is 6 pi 16ths, the other one's at 2 pi 16ths, but negative. Everybody cool with that? How did I pick these points? Because they're not arbitrary. They're my undefines, right? They're my left asymptote, my right asymptote. The rest of this, I'm just going to eyeball it. And because we're sketching, I'm totally cool if you eyeball it. I know that these gaps are the same distance wide every time along the x-axis. Which means I just need to add 3 more ticks in here, right? So here's an easy one. Here's another easy one. Here's another easy one. Again, just to show you, I need 3 points in between here that are equally spaced. That's these 3 points, but I don't want to have to take the time to get it. If I know they're equally spaced, that one is equidistant from these, right? And let's just do it again. I'm cutting this just like we did the other one into 5 pieces with 4 cuts. All right. Now what? Say it again. So the y-axis, oh, sure. Because we're sketching, I'm just going to say, here's 5. It does say 18. I'm going to zoom away and it's going to look blurry for a second, but I'm trying to write small here. But that will be fixed. All right. I did say 18 there. That's just a typo. Or, here's your fun, okay, here's a fact. Typos occur when you're doing what?
Like thinking about something else.
So maybe, but when you're typing. What do you call it when you make a mistake when you're writing? Because a typo doesn't really make sense. So a righto makes sense to me, but it sounds kind of dumb. Like, I agree with you. This is like the lamest fact ever. A scribal error.
I was going to say a writing mistake.
Writing mistake would also work. Scribal error. I will henceforth call them rightos. Cool. All right, so we have these guys. I'm going to add these purple lines on mine. Just kidding. I'm going to add these yellow lines on mine to represent the whats? Asymptotes, where it's undefined. Now, if I want, and I do, how many periods do we really show of this? Every time we're graphing, we're always going to show, anybody remember? 2 periods. So here I am working out another one. I'm just going to make these ticks equally spaced. And I know that it goes 1, 2, 3, 4 to it. So here we go. 1, 2, 3, 4. I have another asymptote right here. I can sketch my second period without ever even having to think about what the values are. Okay. At this point, all I need to do is plot my points, which seems unnecessarily redundant. But here we go. The first point was at what? 2? On your table, I can't see mine. I think it's 2, right? Would you believe that that's about 2? I believe it. The next one was at 5. And the next one was all the way up here at 8. That is a pretty steep tangent. Okay, tell me what I've done wrong. Don't graph this. It's not a tangent. That's a segment that doesn't mean anything to me. To make it a tangent, I usually start at the middle because it makes it easier for me to do. It curves up and then it spits up because there's an asymptote. It curves down here, hate it. It curves down here, still hate it, because it's a tangent. Now, do I even have to think about the next one? I know that one tick away it's here at 2, another tick away it's up at 5, and another tick away it's up at 8, just like our other one. And here we go, the second period of this tangent function. Now, you will find that sometimes when you already go through your graph and make it, you don't have enough space for this. So hypothetically, I'm just going to show you what that would look like and what it's okay to look like. Is it possible that you've done this on your page and unfortunately you only went this far but you don't have any more space to do it?
It's very possible.
It's certainly possible, and I guarantee it happens at least once. If I want another period, I don't say it has to be another full period by itself. I know that the function will do this here. It will do this on this side. Do I have another full period of tangent showing? I just have half of the period on either side of it. There's still 2 showing. I'm good with this. Cool. Feeling okay, feeling awful with tangents. Okay. I am going to summarize this, but instead of me just talking at you, we're going to do a quick check. I want like a real number, like a real one. How do you feel on a scale of 1 to 5? If I asked you to graph a tangent, I could, I couldn't. 0 says, nope, I can't even write the word tangent on my page. 5 says, I could do this in my sleep. Give me a number in between. Don't. Rather than me saying that we're just gonna like lecture at the rest of them, I think we can make sense of it. I have a few simple questions. And you do not have to write this down, but I want you to talk with these out, and then we're gonna summarize, and it's gonna go much faster because I don't think we really need to build it up because it's the exact same process, just with a different function. Okay, few questions that I want you to address. I'm gonna give you like 5 minutes. I would pick somebody in your team to work as your scriber to write this stuff down. Cool. Okay, first question. What would change with cotangent of x? Okay, that's our first question. There's a lot of stuff that changes. We'll summarize it together, but I want to see what you guys come up with first. Okay, I lied. Instead of doing a bunch of questions right now, this is a question. I'm going to give you like 2 minutes. Talk it out, write down. Somebody in your group, write down. It can be in the margin. That's fine. What's different about cotangent? And I'm going to start getting ready for just blasting through it. This is the updated question for anybody watching it. Where is it undefined? Tangent is undefined at pi halves and at negative pi halves because sine over cosine is 0 there, right? This time, where is cotangent undefined? At pi and 0, or at 2 pi if you'd rather. Or if we want to word it a different way, I think I could say it's at negative pi. Well, hold on. Yeah, we could do negative pi and 0. There's a bunch of them, right? Okay, so looking at this, the easy answer, just without having to think about the unit circle, do you guys agree that this answer is when what 0? Sine x is 0. Okay. Now, as we start thinking about this, what this means is we get a little shift. And instead of going through the entire thing like we did with tangent, because it's the exact same process, we're just going to set it up a little tiny bit differently. Now, for the standard cotangent, it depends on the book that you're looking at. We are going to stay consistent with organization, so I had tangent. We're going to have a follow-up subsection with cotangent real quick. So here's cotangent. And we're only going to look at the parent function because once you have the parent, all the other transformations work the exact same. Period is 2 pi over b. The steepness of it, or your amplitude, is how big of a step you'll take, and your asymptotes move. But let's look at this. If we have the function y equals cotangent x, these ones I do not have locked in as well in my head as tangents, but we can make sense of this. I know that it's undefined in a couple different places. I know that it's undefined at 0 and pi and 2 pi and any multiple of pi, right? Now, we have an option. I can either go from negative pi to 0, which would say that on a scale, if we were to graph this, and we will graph this in a minute, I could either work in this little first section right here without ever touching the x-axis, or we could hit this section on the other side right here to run pi radians. Would you prefer negative pi to 0 or 0 to pi? You want it in the positive side? All right, so let's check it out. The fact that this happens, my table is easy to make right off the bat. If I make x cotangent x and the y value that it spits out, where's the first place that it's undefined again? 0. Where's the last place that it's undefined? Pi. And then it'll happen again at 2 pi and 3 pi and 4 pi. But in both of these situations, I'm undefined. Now, the fact that I can show every value here between 0 and pi tells us the period. I can see what the period is. What is a period, just to make sure? Pi still. Okay, how many cuts would we make in it to determine our jump if I know the period is pi? 4. So I would jump by pi over 4. Everybody cool with that? Okay, help me out here. What's 0 plus pi fourths? Pi fourths. Do it again. Pi halves. Do it again. 3 pi fourths.
Could you say how you identify the jump again?
So when I took, are you okay with saying the period is pi? Because I can only run a half a circle before I get undefined. Like I hit every possible value. If you go between the next one, and I'll look at the graph and we'll see it. But I know that between those is where I hit all my values. I then take the period of pi and I cut it over 4.
Yeah.
Yep. So check it out. I know that cotangent of pi fourths, of 0 is undefined. What about the cotangent of pi fourths? It's 1 again. How about pi halves? How about 3 pi fourths? Negative 1. Whoa. What? 1, 0, and negative 1. I'm sorry. Now, as we're looking at this, some of you guys like very clearly are answering it without having to do a ton of work. Could you describe the work that you did in your head to get these values? Alex, will you describe the work? Because I think you were one of the people that were saying stuff. So whether we're looking at I love it. Whether you're thinking about tangent or cotangent, at pi fourths, when it's root 2 over 2 and root 2 over 2, whichever one is on top, you still get 1. Okay, now, when we take this and we graph this function, it's going to look similar, but a little bit different than tangent, because it's its cofunction. Just like sine and cosine look similar, but a little bit different, same thing's going to happen here. Okay, we have elected to only work up to pi initially. So I'm going to say pi lives right here, and now I have way too much. Now, the scale part is something that people always struggle with. How do I put these other points on? Do I actually have to get out a ruler and measure pi fourths of an inch? No, if you cut it in half, where are we at? Pi halves, which means these smaller ticks are pi fourths and 3 pi fourths. Okay, I'm not going to do the same thing over here, but I am going to go out to negative pi. Now, at any multiple of pi, all n of them, doesn't matter what they are, I know that sine is 0, so I'm going to have undefined, which means I'm going to put what on my graph here at pi? There's a vertical asymptote right at pi. There's one at negative pi, and this one's going to be hard to see on your page. I always draw it slightly next to it so I can see it. There's the one at 0, or 2 pi. They're the same angle. Can we plot these 3 points? So I'm going to do it. At pi fourths, and I'll put a scale here, I suppose. Totally made up, right? I get to pick this. 1 and negative 1 are my choices. Here we go. I like that color. At pi fourths, it's 1. Then it's 0. And then it's negative 1. Oh, that was the best one I've made. That felt good. Does it kind of look like tangent? Very similar. Could I draw another period of this? I can. Show me you can. Draw another period. You're already done. Killing it. Draw me another period of cotangent. Oh, I love the next one so much. Love it. It's here. Did I take a ton of time to make sure it was perfect? Is that okay? Absolutely, we're sketching it. Okay, as we go through here, I'm going to ask about these ones rather than just writing it all down. What's the period again? Okay, one of these I am going to write down. What's the domain of this function? It's a set of x something. What can x never be? Can't be pi, or 2 pi, or 3 pi, or literally any number of pi, right? What was the letter we used yesterday to represent that? Can we just say x cannot be a multiple of pi? This covers literally all of them. What's the range? It's again all real numbers. And we will write the period here. What was the period of this one again? Pi? How about cosine? I know that's not the one we're doing, but what's the period of cosine? 2 pi. What about sine? 2 pi. What about tangent? Pi. Cool. So we see a split here. Is this one? I'm not going to talk about it. Never mind. I'm cool with that. Now, I'm going to throw one more question up. And the nice thing is that we wind up getting very similar stuff. We're going to split the class. We're going to divvy up the labor, okay? Okay. Up through tangent and cotangent. Feel okay? Am I going too fast, too slow? Am I Mr. Goldilocks? What's the deal?
Just write all.
All right, cool. I have a couple more questions because I think we're going to be able to reason this out. We have looked at 4 functions up to now. We've looked at sine, we've looked at cosine, we've looked at tangent, we've looked at cotangent. What are the 2 we haven't looked at? We haven't looked at secant, and we haven't looked at cosecant. So let's think about these. Secant, and cosecant. And I know that this looks awful, but I think that we can just fit our information right in here. You do not have to use the same organizational structure as I. All right. How does secant defined? I know that secant of an angle x is equal to something.
Well, r over x.
So you're good. I want tricky though. I want sines and cosines, or at least one of them in your answer. It's 1 over cosine. It is a reciprocal of cosine, and it annoys the heck out of me that secant and cosine match up when the cos are there. I get it. It's annoying. This is 1 over cosine. Now, when we think about a function, all we ever really have to worry about when we're graphing and trying to do these things is I only really have to worry, is it undefined anywhere? Is this function undefined anywhere? It's undefined where cosine is 0. Okay, we're going to switch gears here. What's cosecant defined as? 1 over the sine of x. With this fraction in mind, or this definition, this reciprocal identity, is this undefined anywhere? Where sine is x. Now, check this out. I'm going to ask you guys to do a bit of the legwork here. First one that I want us to think about. If we have a graph, the domain is kind of easy to pick out. But that's fine and dandy. We can go from tabular to algebraic thought. but I want to be able to go the other direction as well. I want you guys, without graphing it, can you write me the domain of secant x? Now, I'm going to give you a little push in the right direction. What is the period of sine and cosine again? 2 pi. Any gut feeling on what the period of secant or cosecant ought to be? It should probably be 2 pi. I want you guys to identify the domain of secant and the domain of cosecant for me. Talk it out. Be okay with being wrong. I want you to be trying. Please have enough room. I hate it. Cool. I'm going to pause the video. We'll come back together in just a moment. 3, 2, 1.
At the top.
At the top, how many radians is that? So I know that it can't be pi halves right off the bat. Here's where we're going to use our wonderful mathematical minds to make sense of this. It can't be pi halves. Where else does it happen? At the bottom, right at 3 pi halves. Now, here's what I think is easier. From this, at pi halves, how much rotation do I have to go to get all the way down here? How much of a circle have I just covered? 180 degrees. How about radians? Pi of them. If I keep going, I'm going to find again up here, which is another how many radians away? And another pi, and another pi. Every pi radians I go, I'm undefined, right? So as long as I start at pi halves, I know that I'm not allowed to touch any point that is just another pi or n pi away from it. With this idea hopefully locked in, can we do the same thing with cosecant? Where's the first place on your unit circle that sine is 0? It happens at 0. And then you turn how much of a circle to get to the next place where that happens? Another pi. So for this one, we don't even have to start at the pi halves. We just start at n, 0 is what we start at, plus n pi, which I'm just going to call that n pi. Okay. Now, for this, I'm going to try to blast through, and if this is a bad idea, we'll figure it out tomorrow. Like, I'm not too worried about it. Is secant easy to think about, particularly? Like, if I ask for the secant of a value, can you guys think about it perfectly yet? Cosine, is it a little easier? So we're going to look at a graph of cosine real quick, and as long as your ears are open, we're going to see if we can't connect something, because I would like to just do a bit of talking without having to do a ton of writing, for me or for you. So I'm going to go to Desmos. Here it is. And let's think about secant. Right? Is that the first one we had? Let's think about secant. Y equals secant x. What? That's weird. Where does secant come from? Secants are hard to think about. Cosine. That's easier to think about, right? Okay, here's what I want us to imagine. And again, this is one of those points where, like, I really, really need you to get loud immediately if I lose you in this thought, okay? I know that secant is defined as 1 over cosine, and that cosine is 0 right here. And I'm just going to use this graph to do it. Here is 1 period of cosine. Now, they have numbers, that's fine. I'm going to think about it here, and I'm actually going to go out a little bit further. Okay, 1 period with some extra space around it. If we look at secant, and I think about this as a graph, it's 1 over cosine, right? Can you tell me where the graph of cosine has a value of 0? You holler at me when you want me to stop when I'm at cosine is equal to 0. Right here. That means that my function would try to make me divide by 0 there. I can't touch it. We've already identified one of these. Okay. You tell me again when it's 0. There it is. We've identified one of these. Okay. Now, this next little part I want us to think about. If I pick right in the middle, and I know it's hard to tell on this one, But let's get rid of these numbers and make them nice. I know that this is pi, right? That's actually pi halves, I'm sorry. Pi halves is right here, and what's here? Say that again. Pi. Remember, this is which function? 3 pi. I'm going to make a graph that's not got a bunch of numbers on it. I'm going to catch up with you. And we're just going to do it here. Now, the reason I'm doing this is when I graph cosecant or secant, and when you do it, you're never actually going to graph cosecant itself. We're going to use the graphs of cosine and sine to make sense of this. So here we go, without the ugly numbers, mixing it up. Cosine starts at 1, so cosine does this. There's a period of cosine, which means I know here is 2 pi, and here's 0, right? And I can see these values. This was at pi halves. This was at 3 pi halves. It's already flowing better, I think. Okay, I'm going to put the same asymptotes back on. And then we're just going to think about how fractions work. And if you understand fractions, it's going to be easy. There are some nice values on the graph of cosine. For example, right here. That's a really nice value. Okay, as I look at that, that's at pi radians. Are you guys cool with that? What's a cosine at pi radians? So what's 1 over negative 1? Okay, that thought is super duper important. At pi, cosine is negative 1, so 1 over cosine would be negative 1. Now, here's the weirder part. Pick something a little bit less than pi. Just a little tiny bit less. So like maybe we'll do pi fourths, so it's kind of a lot less. What's the cosine of pi fourths? Sorry, let's do 3 pi fourths, I'm sorry. Because I'm in this second interval here. Here's pi, here's 3 pi fourths roughly here. What's the cosine value at that point? Okay, it's root 2 over 2. Now, if we look at this, I'm going to abandon the just thinking on the unit circle thought because I think there's an easier way. As I get closer to 0 here, I have something that's getting closer to being divided by a smaller and smaller number. Now, between pi halves and 3 pi halves, we're on the left side of your unit circle. Cosine's always negative. Do you agree with that statement? Because it's quadrants 2 and 3, right? As you get closer to dividing by 0, what happens with the overall fraction? Something divided by something small, and then something divided by something way smaller. It gets bigger. Now, because it's going to be 1 over a negative, do you agree it gets infinitely negative? Which means as I get closer to the cosine being at 0, the secant should get infinitely small. How about from this side? As I get closer to 0, from pi to pi halves, if I'm looking only in quadrant 2, is it still going to be negative? And all of a sudden, I see that as I get closer to pi halves, it gets infinitely negative. Did I lose you there? So, just in case, we're going to think it out just to show it. Grab your calculators, we'll think in degrees again. We'll do the same thing that we did with tangents yesterday or the day before. I want you to check for me 1 over the cosine of 180. We'll stick in degrees. It's negative 1, right? So let's pick something really close to one of these values. So a little bit bigger than pi halves or 90, for example. Try 1 over the cosine of 91. Okay, so try, I hear negative 97, 57. Okay, let's get a little bit closer to 90 from the positive side. What's closer than 91? 90.1 is way closer, right? Ask 1 over cosine of 90.1 degrees. Was that 57 before? Negative 500 something. The closer I get, the bigger the absolute value is, right? The larger the number. Okay, as soon as I move past this asymptote, my x's become positive again. Between 0 and pi halves, they're positive. What's going to happen if I were to check at 0? What's 1 over the cosine of 0? Let's try again. What's the cosine of 0 radians? Try again. It's 1, isn't it? What's 1 over 1? And then as my cosine gets closer to 0, which I see happening on the black graph, I'm just dividing by a smaller and smaller number. What do you think is going to happen? It blows up. What we see when we graph secant and cosecant is exactly this. Anytime that you graph it, here's my recommendation. Graph the cosine or the sine function, and then on the peaks or crests and troughs of that wave, just put a parabola. Every single time. This is what it looks like when I graph 2 periods of secant. When I looked back, I didn't really make a mistake, but I do want to look at this. Here's cosine. Here's secant. Look at all of my cosine peaks and troughs, just building parabolas. Is it going to be much different if I do the graph of secant x? What would I think about instead of cosine if I'm thinking of, if I think of sine instead, what? Get out of here. If I think of sine x instead, what function am I thinking of building parabolas on top of this with? Hey, they do. To graph secant and cosecant, just graph the sine. There's really only 4 things you need. Sine, cosine, tangent, cotangent. The rest of it comes for free. Cool. I want to see if this is enough for you to make sense of all this. So, you get some practice. Tonight and tomorrow, we have a little bit more going through here. But let's see what I want from you first.
I did put my name on my help.
Okay. And I'll be able to find yours in
Yeah.
either situation.
I don't know. For some reason, I thought I usually forget, but this time I did it.
Okay. Tonight, I want you to try homework 4.6.1 is what we'll call this. Tomorrow's lesson is going to be pretty focused. There's only one main idea that we're going to look at, unless the homework goes really poorly, in which we'll do a few more examples of these. Okay. I want numbers between 15 and 37, and let's check it out. I want you to do 15. Just kidding, it's page 317 first. I want you to do number 15. 19. 28. And looking for a cosecant. 35. Okay. This is only 4 problems. This is not a ton. It is so hard to convince anybody to do this, especially when you're not using your personal money, but it's something that's going to happen in college, I guarantee it. Is it possible that these 4 problems aren't enough for you to feel really comfortable with it? Okay. What might you do if you want additional practice? Add more, right? I would encourage, if you need additional practice, 3 of those are odd, which means Calc Chat is going to have 3 of the detailed solutions. I would not build a table for cosecant or secant. I would build the table for sine or cosine and then build my parabolas on top of it. When you graph it, my suggestion, and what you'll see me do on paper when we eventually have like quizzes and tests, is when I'm actually graphing these, I make these dashed so that I know those aren't the main functions that I'm looking at. I'm just using them as a guide to help me sketch it. I dash sine and cosine. Cool. Let's try this. Travelers, if you're watching this, some of these ideas are complex. I can't get a read. I can only see your facial expressions when your cameras are on. Please let me know if you need to meet up, like if you want to do like a Google Meets or a Zoom call or something to work through a few examples.